Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 5 Part A. Question 1 states, derive in detail how the substitution S equals J omega yields the long-term frequency response of a transfer function to a sinusoidal input. So we are going to start out by drawing this scenario. So in our system, we are going to have some process G. This can be as simple or complex as we want it to be. And then we are going to have an input here, and it's going to have the value of A, which is just our amplitude, times sine omega t. And the Laplace transform of this is A omega over S squared plus omega squared. And then the output of the system is just multiplying across to get G A omega over S squared plus omega squared. And so now that we have our output, what we can do is we can do the partial fraction expansion of this. So we have A omega over S squared plus omega squared times G. This is equal to the sum of, and for G, we just get AI over BI plus S plus what we get from our Laplace of the input, which is E plus Fj over S plus omega j plus E minus Fj over S minus omega j. Now, if we look at our first term, what we are going to end up with is AI times E to the negative BI times time. And when we do this, we are going to assume that B is always positive. And this means that over time, this is going to decay, meaning that our second two terms are really what we're looking at when we want to evaluate the long-term behavior of this system. And so to do that, we are going to make common denominators. So we end up with, in the numerator, when we multiply this by this, we end up with ES minus F minus E omega J minus F J W plus F omega. And then going the other direction, we get ES plus E omega J plus F omega J plus F omega. And then in the denominator, what we end up with is S squared minus S omega J plus S omega J plus omega squared. Now what we can see here is that these cancel out, and those in the denominator cancel out. And so when we add all these together, what we end up with is 2ES plus 2F omega over S squared plus omega squared. And another way to write this in a more simplistic form is just CS plus D over S squared plus omega squared. Now we can take the Laplace transform of this, and what we end up with is C cosine omega t plus d over omega times sine omega t. Now what we want to determine are these coefficients. So we want to find out what c and d over omega are. So to do this, we're going to go back up to our equation, but we're going to sub in this cs plus d over s squared plus omega squared. So we have a omega s squared plus omega squared times g. This is equal to the sum of ai over bi plus s plus cs plus d over s squared plus omega squared. Now we can multiply both sides of the equation by s squared plus omega squared. This gets us a omega g is equal to the sum of ai times s squared plus omega squared over bi plus s, then plus cs plus d. Next, what we can do is enter our substitution, and that's going to be that s is equal to j omega. And when we do this, the first thing we want to notice is that this term is going to disappear, and that's because s squared is equal to negative omega squared. Other than that, we're good to plug this in, and you end up with a omega times g as a function of j omega is equal to c times j omega plus d. Now we can isolate g by dividing by a omega on both sides. So we get g j omega is equal to c over a times j plus d over omega a. Now we know that when we do this, we're always going to have an imaginary part and a real part, and here we can identify our imaginary part as c over a. So when we're looking at it here, we're going to have ij plus r. And those are the variables we're going to use. And we can turn this into c is equal to ia. And for r, we can set this as d over omega a, which gets d over omega equals to r a. So now we can take this and plug it into our Laplace transform. When we do that, we end up with ia times cosine of omega t plus ra times sine of omega t. Then we can factor out the a, leaving us with a times I cosine omega t plus r times sine omega t. Now what we want to do is convert this from what is still a sum of signals into one single sinusoidal signal. So to do that, what we can do is set r equal to m times cosine of phi, and I equal to m times sine of phi. And when we plug that in, we can factor out the m, leaving us with a times m times cosine omega t times sine phi plus sine omega t times cosine phi. Now, what we can look at is that I over R is equal to tangent of phi, since we're dividing sine and cosine, meaning that phi is equal to the arctangent of phi. And when you plug that in to our equation here, we get AM times the sine of omega t plus phi. Next, we can move on to question 2. This states, explain why having a magnitude ratio at a phase angle of negative 180 degrees results in an unstable closed loop response. Once again, we are going to start by drawing our system. In this case, we are going to have some function g. There is an input signal here that goes into the process. The process gives an output. This output signal is measured, and the measurement is sent back to the top. Now our set point is some sinusoidal signal, and it's the same for what's being returned. Now what happens when we are at 180 degrees is that the signal's sign gets flipped. So it's a mirror image of what it should be. And this causes the signal to be negated when it's compared right here. And when this happens, really what ends up going on is that the signal is the same as what our set point, our original signal was, but it's at a higher amplitude. And this happens over and over again as the signal makes its way through the system. And even if you stop putting an input signal in, this will continue on until the system essentially blows up.